Hello everyone and welcome back. I am Mr. Cobalt, and in this video we are going to go over oxidation reduction reactions. So an oxidation reduction reaction is a reaction in which electrons are transferred from one reactant to another. So for example, I have three examples of oxidation reduction reactions. So here we have a metal, iron, reacting with oxygen to form an ionic compound. So the way this works is we have the solid metal that does not have any charge. So the atoms here are neutral. So there's zero charge on the atoms of your iron as iron solid. Same thing with oxygen. Oxygen, there's no charge on the oxygen atoms because they are neutral and there's no separation of charge or anything like that. So these are neutral compounds, but when they react, you form an ionic compound here. And so we know that oxygen is in group 6, so that's going to have a 2 negative charge on there. And we can figure out what the charge is on the iron, right? So if we have 3 oxygens, 3 times -2 gives us a -6. So we need a +6 to balance out the -6. So then that +6 is divided between the 2 iron atoms in the compound. So each one must have a +3. So here we have a 3 positive charge. So you could see right away that there was a transfer of electrons, that you went from 0 to +3. So iron being a metal, and metals like to give away their electrons, therefore iron must have lost 3 electrons here, or a total of 6 electrons if we count both irons. And then the oxygen started out 0, and now the oxygen is negative, so oxygen picked up those electrons. So the 3 oxygens picked up those 6 electrons. So that's where the electron transfer is occurring. So you had electrons transferred from one reactant to another. And so that makes that a redox reaction. And so this is what we call a complete transfer of electrons, is when you go from, your non-charged substances to creating a charged substance, an ionic substance. But the reaction doesn't have to create ionic substances from non-ionic substances to be considered a oxidation reduction reaction. What can also happen is what is referred to as an incomplete transfer of the electrons. So the electrons can be formed, you can form other molecular substances that share those electrons, right? So we have covalent bonds, but we're going from like maybe a perfect sharing of the electrons to very uneven sharing of the electrons. So you get polar bonds, right? So you get this uneven sharing due to the difference in electronegativity. And so because of that difference in the sharing of electrons, one side is going to have a higher electron density than the other side in the bond. Like, so for example, if you form like a hydrogen chloride bond, right? So if I was to draw the electron density like this, so more of the electron density would be around the chlorine than around the hydrogen, because chlorine likes to have the electrons more. So you could, in the reaction, end up getting these uneven sharing of electrons, and that's going to create, a partial negative charge on one side. You're going to get a partial positive side, and so you get polarity, and so that counts as a transfer of electrons. So even though it's not a complete transfer where you're creating ions, it is considered a transfer, and therefore oxidation and reduction would occur. So you can kind of see that here. So you have your hydrogen gas and your oxygen gas. Here the electrons are being shared evenly, right? Because both hydrogens are equal in how much they want the electrons. And same thing for oxygen. 2 oxygen atoms are bonded together, so the sharing of the electron electrons is equal. However, when you form water, you get hydrogen oxygen bonds, and in this case the oxygen is going to have the electrons more, so the electrons are going to be around the oxygen more than the hydrogens, and so this is going to give this a partial negative charge, and you're going to get a partial positive charges on the hydrogen. So you get that uneven sharing of electrons, whereas you had even sharing of electrons, so there's a incomplete or partial transfer of your electrons in this case, but it still counts as oxidation reduction. So we would still count the oxygen as being reduced, and then you would have the hydrogen would be considered oxidized in this case. So that's an introduction to what we mean by oxidation reduction reaction. So here's a way of remembering the definitions. So here, oxidation is the loss of electrons. So if you lose electrons, you got oxidized. So oxidation is loss of electrons. Reduction is gain of electrons. So if you are reduced, that means you gain the electrons. So in this case, the iron went from 0 to +3, so it lost electrons. So in that case, iron got oxidized. Oxygen, however, oxygen went from no charge to a negative charge, so it gained electrons, so the oxygen got reduced. So those are the simple definitions of oxidation and reduction. Oxidation is loss of electrons, reduction is gain of electrons. Now, how can you remember this? There's a couple of mnemonic devices that I often use. So I learned this back in high school many years ago, and it still works today. If you remember oil rig. So oil stands for oxidation is loss of electrons. O-I-S, oil. And rig, R-I-G, reduction is gain. So oxidation is loss, reduction is gain of electrons. So you can remember it that way. When I started out as a freshman in college and I was taking my first semester chemistry class, I had a TA that used Leo goes Ger. So Leo the lion goes Ger, right? So same idea. So loss of electrons is oxidation. Gain of electrons is reduction. So Leo goes Ger, oil rig, either one works. So this is a nice way to remember what oxidation and reduction is. I hope this was helpful. In my next video, I will be talking about oxidation states and how you can use the oxidation states to figure out whether or not you have a reduction or an oxidation or redox reaction. Okay, thanks for joining me. If you like this video, please like it, share it with your friends, subscribe to the channel, make a comment in the comment section, and ring the bell for notifications. Thank you for joining me, and I'll see you next time.